It's not just simple that you just use this thing. We will also apply some important strategy to make the mobility better in FinFET. That already occurs in 45 nanometer, 65 nanometer, but we continue to do this in FinFET, right? What is mobility? I never tell you this, right? But if you have learned solid state physics, you learn that mobility depends on the carrier lifetime and the effective mass, okay, of the electron. How? Not lifetime. This is the mean free path time, sorry. Mean free path. So when your electron is moving from semi-classical picture, they are free and eventually you will hit something, right? Either lose energy to photon, hit other electron, get scattered by the Coulomb charge. So this is the mean free path. I said not path. The length is path, right? I'm talking about the time. So mean free. Hey, how do you call it? I forgot. So the time you spend in the mean free path, okay? How long you spend? If it is longer, yeah, sorry? Before you lose energy due to scattering, yes. If it's longer, then you should have higher mobility. Makes sense, right? Another is M star. I mentioned this before, is the effective mass. The effective mass depends on the band structure, and we talked about that before. We have 6 delta valley in silicon, right? The longitudinal mass and the transverse mass are different. One is 0.19, one is 0.98 M0, okay? So if you are given a material, can you change the mobility? Besides changing, if you are not allowed to change the dopant, if you are not allowed to change the surface roughness, you basically cannot change the mobility, right? Unless you engineer the material. And how do you engineer it? You can try to increase the mean free path time or reduce the effective mass, right? So, make sense? But how do you do that? Okay, find a new material. If silicon is not good, let me get germanium. The hole may be good. The mobility in germanium for hole, electron is lousy, right? Then I use germanium for PMOS and then use silicon for NMOS. That was an idea developed many years ago, right? Now they become silicon germanium due to engineering reason and fabrication reason, but with different mode fashion, different composition of silicon germanium. Great. Another possibility is to do the string engineering. How do you get the mean free path time and the effective mobility? It's just a result of the calculation of the lattice. Because your atoms are arranged in this shape with this distance, and then you get this band structure, and then you get this effective mass. And because you have this value, you have this amount of scattering. Because scattering is a quantum mechanical scattering. If you don't have the available states, or you have a low density of states, then you might not get a lot of scattering. That's interesting, right? So if you're walking, anyone can knock you off. But let's say the only way you can knock off is to knock to that building. Then not everyone can knock you off unless something very energetic that can knock you to another street, right? Otherwise, no, you never lose or absorb energy from other people because it's a quantum mechanical one. Okay, so we can use string engineering. Why? Why string? You change the distance of the atom, then it's just that you make a new material. Once the distance is changed, all the band gap shape will be changed. Then your mean free path time, the effective mobility will change. So that is called string engineering. So let's just quickly understand a little bit what is the meaning of string and stress, right? So if I have a bar, this is a crystal, and this has some area, A. I try to apply a force to it, F. Of course, I cannot let I'm not going to move my chip, right? All the way, right? You need to stay at a place. So in order to apply a stress, you definitely need to apply force in opposite direction, just like how you stretch your rubber band, squeeze your rubber band. This is called stress. There are different types of stress. I only give you something simple. We call it sigma equals to F divided by A, force per unit area. That is the stress. Okay? Now, because of the stress, you can expect the material is going to get elongated in this case. Right? There's no... You may see this delta L. This is L. Because of the stress, it becomes larger. Correct? Yeah.
What if the force is in the opposite direction on both ends?
Opposite mean in the same direction on both ends? You mean all pushing to the left?
Like the right is
Yeah. We'll talk about that. Yes. So then what is this? This is string. Right? Usually we use epsilon. It's delta L divided by L. Okay, so you can tell your parents or a friend, wow, the exam is a big stress to me, and now I get shorter because of that. I have string, right? So you don't have stress. Stress is something applied to you. You change yourself, it becomes a string. It's not a good analogy. But that is the meaning of string. So stress, usually we will have a unit of gigapascal that we learned before. Pascal is Newton per meter square. String has a unit of percentage. String bar is 1%, which is a big deal in solid state physics. Think about you reduce the width of this table by 1%. That is a very huge force. You may actually crack it before you can do the string. So string stress engineering can induce defect or reliability issue in silicon. Okay? Now he asked me, what if this force is pushing against each other? What will happen to the delta L? It will be negative, exactly. So that's why here it brings us to another topic. We have compressive and tensile stress. Okay? When the epsilon is larger than 0, then this is a tensile string, right? And of course, the corresponding stress is tensile stress. You're pulling it away. And when it is less than 0, then this is a compressive string or stress. Okay? So here I have the force going in this direction, and here I have the force going in this direction, like what you said. Okay? That's one thing. This is a simple string and stress. We can have many complicated things, but one thing I want to mention we usually encounter is the uniaxial and biaxial. Uniaxial is just like what I showed you earlier. You only apply it in one direction. Okay, so in one axis, uniaxial stress result in this uniaxial string. Okay, this is uniaxial. Biaxial is like this. You try to apply the string and stress in both direction. You just pull it, right? This is very a torture actually. Well, I just pull every direction. But now, you should already know what will happen. If I push this one in uniaxial, the atomic spacing will increase in this direction. How about atomic spacing in another direction? Do you think it will increase or decrease? Some people say it's not going to change, right? Some people say definitely not increasing. Usually it will decrease, right? That's called the Poisson ratio. But you should have this feeling. Give you a rubber band, right? You pull it away, actually it becomes thinner. Isn't that a string in the orthogonal direction? Yeah, so you do have this type of so-called Poisson ratio. Is talking about you pull in one direction, how the other direction change irrelevant to that direction that you are pulling. Okay, Poisson ratio of 0 means that the other direction does not respond to your stress. Okay, good. So we want to understand this. Now, then here I want to introduce some concept how we introduce string and stress. In experiment, it's very easy, kind of. In the past, when people in the university or company, they do experiment to find out how the stress affect the mobility, they just take the wafer, right? This is a wafer, maybe 4-inch, very big. They deliberately maybe put this on an anchor, and then you push a force to it from top. Then as a result, your wafer will bend. But again, you don't bend too much, right? Because you're going to break it. However, just a little bit is enough to go to gigapascal, as I said earlier. In order to let it bend a little bit, you need to apply a lot of stress. But there is experiment. Usually you don't do this in fabrication because after you fabricate your die, you want to have something really pinned on the package. And then with this gigapascal of stress, your package probably cannot withstand with that, right? So what do they do is, for example, this is a planar technology, however, right? They deposit a film, nitride. So because nitride and the substrate have different thermal expansion coefficient, what it means is that when you change the temperature, your material is going to expand or contract, right? Some material expand and contract faster than the other. So you start at very high temperature. You deposit the nitride, okay, there's no stress because you deposit means you just grow chemically, right? Then you cool it down. If this nitride actually, what will you do? It will tensile stress, then it
Shrinking as fast as silicon?
Sorry, I got confused. Then the tensile stress means that it's going to have a, it is under tensile stress, okay? The nitride is under tensile stress, means it's getting pulled away by, it feels itself. If you are a part of the nitride, you feel you are being pulled away. Okay, so why you will pull away? Because when you cool down, you contract very fast. So think about that. Silicon does not contract that fast, but you contract very fast. Isn't that, then you feel that the silicon stop you from contracting, then it means you're being pulled away. Very difficult to think, right? Think about that. Like you have two array of people, right? And then they have an interface, and then one group of people actually shrink very fast, and the other group does not. Then the one that is shrinking will feel that the other group is stopping you from shrinking, means they're trying to pull you away. And they have opposite effect to each other. So if the tensile, eventually at room temperature, this is at tensile stress, then what does it mean? Then it means you are going to compress the underlying film, right? Now, so when you try to compress, look at this, because these are close to it. This one and this one are close to it. So you are trying to squeeze these two. You try to squeeze these two, right? So squeeze it. Two. And then as a result, you will have a stress pulling these two apart. Because this part is far away, so you can ignore the effect to first order. Ignore the effect of this one to here. Okay? So it's just as if, right? I will erase it later. You don't have this part. Because they are far away, right? So you don't affect the channel here. Do you see what I mean? So and then now this is a tensile stress. On the other hand, it means you try to compress this whatever underneath. Make sense?
I guess the objective when you do that is stress in the channel. That's what
Yeah, but I will explain that later. Just follow me. I have this tensile stress film. This part can be ignored because they are far away from the channel. Is this okay? So you delete this part. And now I have film here and film here. they are under tensile stress. It means that they will try to compress whatever in the bottom.
Only there.
Only there, yeah, because these are gone, right? These are removed. This is infinity. Assume it's infinity. It doesn't matter. If your frame start from here, isn't that you will try to compress this whole thing, make it smaller? Yeah, everywhere. Just try to compress. So this one was maybe originally this is like this distance, and then you try to change to this distance, right? Because you're compressing. Is everyone okay with this? It was like, I'm going to erase it because it's difficult to see. But I'm saying originally it is this Y, and because of the film, it will try to compress the bottom to be this Y. Similarly for this part, when it was this Y, you try to compress to this Y, right? Then for this part, which doesn't have any nitride on top of it, what does it see? It feels that you are pulling me away from here. Then as a result, your channel get a tensile stress, right? And then you have a higher mobility for electron. For electron, we actually, it has a higher mobility if you have a tensile stress. Okay? That's just the physics you agree with. You need to agree with me, right? So this part is compressive, right? This part is under compressive stress because, right, it's next to the tensile, right? If you try to pull me apart, I'm going to compress you. We are in opposite direction, yeah?
So then, where you're getting compression, your mobility will be lower. So,
but it doesn't matter, right? Because transistor, the most important part is here. Here you assume that you have very small resistance, right? Transistor is here that dominates the current in the old time. Yeah.
That's why you're pulling the channel apart too. Right?
Yeah, the goal is to pull the channel apart so that here is under tensile. And your electron, your main resistance when it is turned on are the electron traveling under here. That's why you have a higher mobility. But if it is whole, we will use another method to do compressive for this region, but not stress nitride, because the stress nitride usually is tensile. Okay? Yeah.
almost stress.
Yeah, we can do that, but we only discuss this for now. Yeah, the effect is very complicated because it's anisotropic. Okay? So you can stress in any direction. So here, just to show you like what you are saying, right? How about in and out of screen? So this is the FinFET. Do you see it? Right? So this is the source, this is the drain, this is the gate, and this gate wrap around it. Now, all here I want to number are not important because it really depends on channel orientation and technology. This can be outdated or is not universal, in my opinion. Some may be okay, right? But I just, as this lead to what you said, the stress, this is the stress, does not need to be in one direction. You can be in XX. Here is talking about in the XX direction, you have 290 megapascal. In the YY direction, which is across the width, you have 350 megapascal. And then in the Z direction is negative. What is the meaning of negative? Compression. So, which makes sense, right? It's very difficult to have tensile in all directions, which is possible. But if you just rely on material, then one of them need to be in compression because of the Poisson ratio. Right? So the whole idea, I just want you to know that stress comes in all orientation. That's perfect. And then because of this, you have different improvement in the mobility for NMOS and PMOS, and also on different orientation, not channel, I mean the surface orientation. No need to study the numbers. Yeah.
I was just curious, so for example, say for 110 direction for NMOS, you get pretty good 25% ability. But compared to the non-stress device, what is the percentage in lifetime reduction of the device?
There will be reduction.
Last with one, right?
In principle, you won't last as long. Yeah, but they do it such that it's enough for the device lifetime in the market, right? So your iPhone all has stress, but they never fail. They probably fail before you drop it on the floor. They might do the probability, yeah. Yeah, because you are just different physics. All this mobility, there is the effective mass and scattering are very different for NMOS and PMOS. Electrons run in the delta valley, and PMOS are at the gamma valley, which has light hole, heavy hole. They are very different physics, so they are not symmetric. Yeah. Okay, so this I just copy from the paper. So they derive a theory to calculate how the mobility changes with stress. So from experiment, they actually cannot measure the stress, right? So they can measure the percentage improvement in current. And then they propose their theory. Based on their theory calculation, they get this stress. And based on the calculation, they also get this mobility to say that, oh, my theory match experiment pretty well. Yeah, so you can ignore all this because you're not doing research in this area, so no worry. Okay, I just only take away is this sentence. Understand there are three directions of stress. And even more, we did not talk about the so-called shear stress. Now we're only talking about the orthogonal stress, but you can have shear stress. Just for those who are very interested. If you have a square like this, you actually can apply the force in this direction, but make it but don't let it rotate, right? Then you're going to have a shear effect. And that has a big impact also on many things. Okay? Let me just write this down. Okay. Okay, so then how do you do stress for PMOS? Well, we want compressive stress, right? So what you do is to make the source string atom larger. So you make silicon germanium source string. Germanium has a larger lattice constant. Very little larger, not much. How much is that? Less than 10%, about 5%. And this gives a very big deal because in material science, a lattice mismatch of a few percent can stop the crystal from growing already. Okay? So here is the germanium. If you have germanium, when you grow the lattice, of course this is a cartoon, right? You don't have this lattice. You will try to align atom to atom. Germanium used to be large, 5.646, and then you align with a kid, 5.43. Think about that, the kid, each of them just pulling the hand, and then the adult try to have the maximum distance by pulling the hand, and then the kid need to touch the adult here, and they also need to pull the hand against each other, hold the hand against each other. There isn't the kid will get pulled away. Do you understand what I'm talking about? Oh my God. For example, if I have an adult, big adult, and they need to hold their hand, right, this is their hand. Right, they hold to the maximum. And in front of them, they also have a kid, and they also need to hold their hand to the maximum. Now, but you also mandate this kid need to stand in front of the adult. Otherwise, you get punished. Isn't that these kids are going to have a lot of tensile stress because you need to stand in front of the adult, while at the same time, I only have a shorter hand to hold each other. This is just like this case, right? So the silicon is going to get compressive stress. Tensile stress, sorry, right? Because your silicon are the kids, they are smaller, so tensile, right? And this is going to get compressive stress itself, right? So this part is compressive because I have more silicon, more germanium. This one is tensile. Oh, so it's completely wrong. I cannot say in this way. This will confuse you. This is this is talking about the corner, so it is correct because here is about the corner, right? The corner you do have this effect, but I should not highlight this. But the corner is just to tell you that, yeah, this is large, this is small, so this one got tensile stress, but this is at the bottom. That's not what we are interested in. I want to highlight is this region because your silicon germanium is larger, right? If you fix this boundary, you do something to fix it, then it's going to push inside, right? It's just like this is the wall, and then you keep filling in add out, then of course you're going to squeeze the kids in between, right? So here you will get compressive stress in the channel. Make sense? Yeah.
Doesn't doping also cause stress?
Yeah, doping will cause, but usually doping is low. 1E20 is like 1 in every 1,000 atoms. So at that level is not what we are interested in. Here is talking about percentage, like 10% of germanium means every 10 silicon atom you have 1 germanium. But doping is talking about every 1,000 silicon you have a boron. But if you have really heavily doped device, region, you do have this stress effect. People study that. Depends. I think they do use, I don't know, they do use silicon germanium. Depends on the technology node. Yeah. There are many other ways, but I don't know them well. But definitely silicon germanium is one important method to do compressive stress. And then this nitride stressor is a method to do the tensile stress. This was done very early 2000. People tried that already. Okay. Now, then, let's go back to FinFET. This is FinFET. But you say, well, why is it so ugly? Because it is cut into half. Imagine that I cut into half. This is source, this is drain, this is the gate. Right? I cut into half. Do you understand what I mean by cut into half? It's just like this is the fin. I cut away the other side. So this is the fin. I cut away this side. Okay, I just chop into half. Right? So let's just quickly take a look. For example, here is say SL has negative 2 gigapascal. Right? This is megapascal, so it's 2 gigapascal. Very huge stress. SL, what's L? L means along the channel. So if I did not say it, but here I show you, is in the Z direction. Right? We define this is the Z, okay? Just a definition. So we have a very strong compressive stress to the channel. Do you see that? And if you look at here, stress ZZ is negative, means compressive. A lot of the region are between -1 to -4 gigapascal. Now, for the same place, I can turn on whether it is stress YY, means that it is in the direction cutting across the fin. Then you see that they are actually not that large, a little bit tensile stress. 400 gigapascal is not much compared with 2.5 giga, 400 mega compared to 2.5 giga. So in X and Z, they are all in tensile. They are going to affect the mobility, but the main point is that the compressive along the transport direction is going to enhance the whole mobility. This is PMOS. And this is the one I show you here. But this is the bulk MOSFET. Here is the FinFET. And how do we do it? We have a 50% germanium. Every 1 silicon, you have 1 germanium, right? Instead of 1,000 silicon, 1 germanium. So have a huge compressive stress. Any question?
Is this simulated in Centaurus?
Yeah, that is a Centaurus picture. They are simulated there. Okay. Then how about for NMOS? For NMOS, you can use nitride, but not easy and not effective. So for FinFET, what you do, instead of silicon germanium, use silicon carbide. They're all from the same group, right? Group 4. Carbon, silicon, germanium, atom gets larger and larger. Carbon is smaller than silicon, right? So naturally, you will get tensile stress because if this is the fin, And then this is the source string. And here I have a silicon, carbon, silicon, carbon. This is small, right? If I fix the boundary here, you can think about I do something to fix the boundary. Right, this is the boundary. Fix. Sorry for the pen. We fix the boundary. Then I have so many small atoms, it will try to contract to this side. Then as a result, you apply the tensile stress to the channel. And that's what you see here. You have about 7 megapascal of tensile stress. Yeah.
So how is carbon implanted here?
This is, they usually use epitaxial growth. They grow it, okay? When you deposit the silicon, then they add the carbon in the precursor. SiGe is just like you have silane and germane, right? Silane SiH4, germane GeH4. You have these two gas and let it deposit, then they grow silicon germanium. Yeah. No, though, when the carbon is incorporated in the silicon. I mean, it cannot, I mean, depends on what you mean by dope, right? Usually when we say doping, we try to add the donor or acceptor so you become active, right? You can donate electron or hole. But carbon and silicon, they are both wavelengths equal to 4, right? So you don't have this electron or hole, donor or acceptor, but you do put them there so that they substitute the silicon, but they don't substitute equally. Think about this classroom, right? You have everyone dressed in black, and then someone comes in, kick out one student, and he or she dressed in blue. But you are not going to have black, blue regularly. You can have a place that you have a little bit more red, a place more blue, but overall, you have a certain percentage, but they are all sit neatly in the chair, in the lattice. Okay, this is called alloy. So this is actually alloy. Okay. Okay, good. Now, just give you some number. You see that, as you just asked, right? How do we get this doping, right? Or dope, I just call it doping. This silicon germanium or silicon carbide, right? Is that you need to grow the epitaxial layer, right? So here show you some of the shape and typical angle and typical number. No need to memorize, just as a cheat sheet. If you in the future you want to take a look, you take a look. Okay, because if you leave this school, you might not have. This is from the application note from Synopsys Centaurus. You can find it there. There's an application library, right? After you've done assignment 1. If you did not, a lot aware of that, then you did not do it. But anyway, yeah, okay, yeah.
So actually, it sounds to me like doping and epitaxy are two different processes. I mean, at the end of the day, they're doing maybe the same thing. You're implanting something.
Yeah. Yeah.
But they're
implantation. But no, I don't want to distinguish doping and epitaxy. I would distinguish epitaxy and implantation, right? You can grow it while you incorporate those dopant, or you can grow the what do you call the base material, and then you do the implantation and anneal it. Okay.
implantation.
Epitaxial growth, yeah. It's just like you can either let all the students who dress in blue come in first and sit here, and then just let some student in red come in and kick out some of the blue and sit there. Or when you start filling up the classroom, you let the blue and red come in at the same time. Each one find your seat, right? The blue and red, okay? Okay, so the last thing I want to talk on about this topic is the threshold voltage of FinFET. So for bulk and planar, in order to achieve the threshold voltage we want, we usually need to have a very low work function for the NMOS and high work function for PMOS. That is usually how we do it, right? Because the threshold voltage proportional to the metal work function minus the built-in, how do we say, silicon? Yeah, the substrate Fermi level. Okay, of course with other terms like depletion term or whatever. But if you have a higher metal work function, then you will have a higher threshold voltage. Yeah.
What's the general definition?
Work function is just the Fermi level in metal. So what is work function? Just go back to the basic physics. You have a metal. How much energy do you need to extract an electron from the metal to the vacuum? That is the work function. Okay? So, and then in the band diagram, it is just your Fermi level. Not Fermi, Fermi level to vacuum, the difference. That is the work function. Okay? So, because FinFET are undoped, and also they are thinner, they lack the depletion term. If you remember, the threshold voltage depends on the phi ms and also the depletion term, etc. They don't have that, right? So just take it for granted. Trust me, you need some gates that has a work function closer to the mid gap of the silicon, right? So this is the conduction band edge. This is the valence band edge of silicon. Right, so since we are not going to discuss this in this class, just memorize this. In the old time, if you just use N plus gate, then you will have a better, pretty good, well-behaved NMOS. P plus gate for PMOS, you have well-behaved PMOS. But if you apply this to the FinFET, it won't work because the FinFET usually is undoped. It is thin. It doesn't have the depletion charge. So you need something closer to the mid gap. You cannot get this by using polysilicon. So you are forced to find special metal for that. So in early 2000, there was a big research effort to find the metal gate. For a few reasons. One reason is for FinFET. And indeed, at that time, with my PhD research, I also did something called nickel silicide. And we want to use nickel silicide with different doping before silicidation to adjust the threshold voltage so that it is in this region. But obviously, it's not that successful, right? Because now no people use nickel silicide for the gate. We also try molybdenum, but with nitrogen implantation. So many things, right? But nowadays, it's very mature in the industry, and they do this gate work function engineering by deposit a few atomic layer of different metal. Then they have different effective work function to get what you want. NMOS, PMOS, high voltage, low voltage on the same wafer. Yeah.
There's no.
No. Polysilicon is gone since 45 nanometer. Because polysilicon has a very strong gate depletion here. Now you're helping me on that project, right? So you will see, you should see the gate depletion effect. So I won't go into detail, but the point is that the doping is low, then as a result, you have so-called gate depletion. Yeah. It depends on the gate. Oh, you mean for the gate? Then depends on the technology node, if it's 22 or I think so, yeah. Yeah. Say again, the what? Oh, yeah. So let me say it clearly, right? So this is the old technology. When you have bulk, you may have N plus polysilicon, and this is silicon, this is N plus, this is N plus. So this is a good transistor. But now when you have FinFET, I treat it as a double gate. Then you have N plus, then you have two oxide, and then you have this, right? This is metal. This is metal. Metallic, yeah. maybe titanium nitride. I don't know what they have here. Then this is a good transistor. If you try to apply polysilicon to it, then your work function, your threshold voltage will be too low. Apply P+, then you will be too high. You need to have something in this region. Okay. Okay, so confinement is like SOI. I don't want to talk about it, right? Because you just two gates, right? Last time SOI, what's the difference between SOI and this guy? This is silicon, and then you have box, right? So this is SOI. And now the only difference is you still have silicon, but then you have just a thin oxide at the bottom. And then you have two gates, right? You have two gates. Right? This is FinFET or double gate. Okay, so the theory is the same. Now then, I do want to go over something a little bit quicker because maybe not necessary to